Welcome to the poster presentation of our paper on greedy channel selection for dynamic spectrum access radios. My name is Alex Lackbor, and my co-authors are Jaime Rivas-Ray, Professor Jeffrey Mainland, and Professor Kapil Dandekar. We are all affiliated with Drexel University in Philadelphia, Pennsylvania, in the United States of America. As an introduction, we recognize that dynamic spectrum access, or DSA radio networks, use radio frequency, or RF, spectrum sensing to evaluate the viability of the opportunistic use of radio channels. Secondary DSA radio networks are typically expected to follow a polite do-no-harm policy, or spectrum etiquette, to avoid creating excessive RF interference to primary users. Under this policy, secondary DSA radio networks must avoid using a radio channel after detecting a primary user is in that channel. However, in a congested RF spectrum scenario, DSA radio networks may not be able to find clear white space spectrum and therefore need to adopt a competitive or greedy spectrum usage policy in order to achieve the performance goals of the radio operator. Due to the possible degradation to a primary user, this competitive policy is reserved for public safety or military radio networks that have a special spectrum regulatory authorization. Prior work defined the concept of partially occupied gray space spectrum versus clear white space spectrum in reference 1 shown below. However, that work did not describe a method to evaluate which frequency channels should be prioritized for use in a competitive operating scenario. Our paper describes an algorithm that calculates a variety of RF interference metrics for each of the DSA radio channels and ranks them. We refer to this algorithm as the Greedy Channel Ranking Algorithm, or GCRA. As we will show through an analysis of experimental results, the pre-detection average interference power metric was found to be the most accurate channel ranking metric in terms of predicting which set of DSA radio channels had the highest data throughput. This slide shows how the GCRA is integrated into the architecture of a generic DSA radio. Starting with the radio hardware at the bottom and following the processing flow in a clockwise direction, the DSA radio provides a block of RF samples to the GCRA, which then extracts interference metrics for each radio channel and ranks a set of radio channels according to a single interference metric. The set of ranked radio channels are then used by the DSA radio's radio resource planner for making decisions about which channels the radio should use or avoid in order to competitively maximize throughput of the radio. The optimized channel plan is then sent to the DSA radio hardware so that it can reconfigure its radio channel. It is expected that the GCRA will be executed periodically as part of the DSA radio's channel optimization process, especially when the RF environment changes due to radio node mobility or changes in radio network traffic. This slide shows the flow of signal processing operations in the Greedy Channel Ranking Algorithm. In step 1, a time-frequency spectrogram transform is taken on a 1/2 second of RF samples collected by the radio hardware. In step 2, the spectrogram pixels for a single radio channel are extracted for further processing. In step 3, demodulated DSA radio network bursts are removed from the channelized spectrogram pixels. In step 4, a spectral shape detector is used to detect and remove the pixels of any remaining OFDM modulated radio packets that are unique to the DSA radio network. In step 5, a multimodal statistical analysis is used to detect interference samples above the receiver's thermal noise floor. In step 6, a variety of interference power metrics are calculated, including percent occupancy, average interference power pre-detection, average interference power post-detection, interference energy, and predicted EVM. Due to time constraints, we will not define these interference metrics here and refer the audience to our conference paper. In step 7, the DSA radio channels are ranked according to a single user-selectable interference metric. The Drexel University Software-Defined Radio, or SDR, testbed contains over 40 SDRs and can either test over the air with antennas or using a 24-port mobile RF channel emulator. As described in more detail in a later slide, we created a radio link using our Dragon Radio SDRs and measured its throughput performance on a variety of interference scenarios. Reference 2 describes the architecture of our SGR testbed and the design and performance evaluation of the Dragon radio. In Step 1, the spectrogram is calculated for a half-second block of RF samples collected at a sampling rate of 10 megasamples per second. In our example DSA radio network design, each DSA radio channel has an instantaneous bandwidth of 1 MHz, and there are 10 adjacent frequency channels multiplexed across 10 MHz. As shown in the spectrogram, radio channels 2 through 7 are occupied with burst emissions from our DSA radio network, and all of the other RF bursts are considered other user interference. In Step 2, the spectrogram pixels for channel 4 are extracted for further processing. This slide shows the spectrogram pixels for channel 4 that spans 1 MHz of the DSA radio's full 10 MHz operating bandwidth. In Step 3, spectrogram pixels that are known to contain our own DSA radio network bursts are removed before calculating channel interference metrics. This slide shows the spectrogram of channel 4 after removing demodulated DSA radio bursts. Unfortunately, not all DSA radio bursts were successfully demodulated, and it is evident that there are some residual bursts that remain in the spectrogram shortly after 50 milliseconds and shortly before 450 milliseconds. In Step 4, an OFDM spectral shape detector searches for our DSA radio's 1 MHz wide OFDM bursts and removes those pixels. It can be observed that the DSA radio bursts that occurred shortly after 50 milliseconds and before 450 milliseconds are almost entirely removed, and any residual power adds an insignificant amount of error bias to the interference metrics. In Step 5, a histogram is calculated on the remaining spectrogram pixels, and the detection threshold is set as the geometric mean of the mode of the noise floor power and the lowest mode of the interference power. In Step 6, the interference samples are used to calculate a set of interference metrics that include channel occupancy and average interference power. In this example, the estimated channel occupancy is 30.7% and the average interference power is negative 69.8 dBm. In order to evaluate the GCRA's ability to predictively rank the DSA radio channels in congested spectrum, we decided to conduct a laboratory experiment. The goal of the experiment was to assess which interference metric offers the highest predictive accuracy for ranking channels in terms of DSA radio data throughput. The experimental approach was to synthesize a set of 8 bursty interference sources with a variety of center frequencies, bandwidths, duty cycles, burst durations, and power levels. See the enumeration of the 8 interference waveforms in the spectrogram on this slide. The composite RF interference waveform is designed to span most, if not all, of the 10 DSA radio frequency channels. Then, we place the antenna of the composite RF interference source near the antenna of the destination DSA radio that is running Drexel University's software-defined DSA radio stack. See reference 2 below for more information on Drexel's software-defined radio design. The RF interference source is then set to transmit the composite interference waveform in a continuous loop for the duration of the test. We then iteratively tune the pair of DSA radios to each of their 10 radio frequency channels and measure the average throughput performance of each channel. Finally, we calculate the channel ranking accuracy by quantifying the agreement between the channel ranking based on measured throughput, otherwise known as the ground truth ranking, versus the channel ranking based on each of the interference metrics. 9 interference waveforms were used for the laboratory experiment in order to generalize evaluation of the GCRA's accuracy. Setting the TX gain values to 0, 10, or 20 dB sets the overall analog transmit gain for each of the composite interference waveforms. Setting the seed values to 101 or 106 was used to predictably generate 2 random composite interference waveforms. Including the 3 tests with the equal power designation constrained each of the 8 interference sources to have the same average power. We note that there is a large performance variation for each of the DSA radio channels and each of the interference scenarios. We also note that the interference source's TX gain is anti-correlated with the throughput on each channel, as expected. Initially, we calculated the percent error for obtaining an agreement between the predicted channel ranking order and the ground truth ranking order based on measured throughput. However, this resulted in a high average percent error, and we concluded from this analysis that the correlation between the interference metrics and the throughput performance is too low to obtain exact ordered channel rankings. Therefore, we developed a justifiable alternative metric that evaluates the degree of the intersection of the set of n best channels ranked according to a single interference metric and the set of n best channels ranked according to the measured throughput. The figure on this slide shows the average percent prediction error for each interference metric versus the number of channels in a comparison set. As can be seen in the black trace with the circle marker, the average pre-detection power is the most accurate metric for predicting the best set of channels for up to 3 channels at a time. This is an intuitive result because this metric includes a representation of the duty cycle of interference within a radio channel. In conclusion, we demonstrated through a limited laboratory experiment that the greedy channel ranking algorithm has sufficient accuracy to predict which set of n channels should be selected or avoided by a DSA radio in order to maximize its competitive throughput performance. The most accurate metric for selecting the set of n best channels is the average pre-detection interference power. This metric has a low computational complexity and removes the need for introducing the complex signal processing operations in step 5 that focused on detecting which spectrogram pixels contain RF interference. In future work, the prediction accuracy of GCRA should be tested over a large set of realistic interference scenarios to observe and mitigate possible edge and corner cases. We also plan to introduce more sophisticated performance prediction techniques and develop an approach to predict the exact order of the DSA radio channels that maximize competitive performance. Thank you for your time and attention. Please contact us with any of your comments or questions.